So last lesson we started talking about conditional probability. So that is where an outcome depends on something else. So you might need event A might be more likely to happen if event B has happened. So the common way to look at that is normally if you looked at, let's say, what sport someone plays compared to their gender. So if event A is playing netball and event B is being female, the probability of A given B is a lot higher than just A by itself, because very few males play netball. Okay. Today what we're going to be talking about is independent events. So kind of similar sort of topic. So in the previous section we looked at how an event can be conditional on a second event. The chance of a student playing netball or soccer will be affected by their gender. On the other side of that, coins are what we call independent. What you get on the first flip of the coin doesn't affect what you get on the second flip of the coin, doesn't affect what on any other flip of the coin. Same as rolling a dice. I know people that play games that involve dice rolling. If they get a dice that rolls like ones a lot, they throw it out. Bit silly, I think, because dice are expensive, but there you go. Okay, so independent events are events that have no bearing on one another, and therefore they don't affect each other's probability. So an example of this would be when you flip a coin, your chance of getting tails is not affected by the height of your mother. Makes sense. So regardless of how tall your mum is, it's not going to affect how you flip a coin. So that would be independent events.
So what page of textbook is it?
Of the workbook, it's the behind what we were up to last time. 45 on mine, might be a little bit different on yours. So if you talk about events that aren't then independent, you might have heard of the Space Shuttle Challenger. Happened in 1986. Basically, there was a little O-ring, like a little rubber ring, that used to help regulate the fuel flow between the rocket boosters. And what happened was they didn't test it under cold, because they're just like, oh, we're going to launch from Florida. It's always hot in Florida. It'll be fine. What happened is they had a cold front come through Florida, and it was like 5 degrees Celsius on the day they launched, which what had actually happened is that little rubber O-ring seized up, and it caused the fuel to not flow properly, and the shuttle blew up and killed 7 people. So that's an example of not independent results. So they would have looked at that O-ring and said it has a failure rate of 1 in a billion, but the failure rate when it's under a certain temperature would have been much, much higher. So that would be an example of dependent events. The failure rate was dependent on temperature. So that being said, in my class, I don't think anything's going to explode if we get an answer wrong, which is good. But we do need to know if things are independent or not. If two events are truly independent, we can state the following. The probability of A given B is the same thing as the probability of A if probability of A and probability of B are independent. So only if that's true. So that makes sense. If event B has no bearing on event A, the probability of B is a given. Sorry, the probability if B is given should not affect the answer. So if we found that, let's say, gender had no impact on what sport you played, so everything was completely equally represented, then it wouldn't matter if you're a male or female when you're looking at the probability of playing netball, because that wouldn't affect the data in any way. So that means the probability of A given B would be the same thing as the probability of A. So if we look at our previous example, the chance of you flipping heads on a coin, we said before the height of your mother and you flipping a coin at independent events, they don't affect each other. So therefore, the chance of you getting heads on a coin is the same as the chance of you getting heads on a coin given that your mother is under a certain height. So because they're independent, the probability of A is equal to the probability of A given B. So we can then make a rule for testing independence. We know that the probability of A given B, you find that by the probability of A and B divided by the probability of B. If they are independent, if A and B are independent, we can substitute probability of A given B equals probability of A into our equation. So that gives us the probability of A is equal to probability of A and B over B. And we can rearrange that to be the probability of A and B. A intersection B is equal to the probability of A times probability of B. So we can say that events A and B are independent only if this is true. So most of that was just to get to this rule here. If my events are independent, that is true. If they're not independent, it's not. So these are our independence tests. If the probability of A given B is equal to the probability of A, they're independent. If the probability of B given A is equal to the probability of B, they're independent. And if the probability of A and B is equal to A times B, they're independent. So that's the way we check. Are there any questions? I'm seeing some very blank stares right now. I know it's sometimes hard even for me up here when I'm speaking, just saying probability of A, probability of B, like trying to keep that all straight in your head. But the 20 words or less version, things are independent if they don't affect one another. If I flipped a coin and then rolled a dice, they're independent. The way I flip that coin doesn't affect how I roll the dice. So what that then means is, for flipping a coin and rolling a dice, all of these three things would be true. The probability of getting a 6, given that I already got a heads, is the same as the probability of getting a 6 anyway. Because regardless of whether I got heads or tails, the probability of getting a 6 is 1 out of 6. Okay? The probability of getting a heads, given that I rolled a 6, is the same as the regular probability of getting heads. It doesn't affect each other. And the probability of both has to be equal to probability of A times probability of B. So rolling 6 times getting a heads. Okay? So, let's see. An experiment consists of drawing numbers from 1 to 8. Let's say A is 1, 2, 3, 4, B is 1, 3, 5, 7, and C is 4, 6, 8. Are A and B independent? Well, we have 3 tests. The easiest one is we can say the probability of A and B equals the probability of A times the probability of B if independent. So if they're independent, that's true. That N symbol, what does it stand for? Intersection. What would the intersection of A and B be? Like, what's the chance of, or what elements occur in both A and B? What's in their intersection? 1 and 3, yeah. And how many numbers total are there? So we're talking about the whole set. So that would be 8. So the probability of A and B happening would be 2, or the intersection of A and B would be 2 out of 8. Do we agree on that? So we got the 2 because we're looking for the intersection of A and B. So the intersection is their overlap. The overlap of A and B, well, A has 1, 2, 3, 4, B has 1, 3, 5, 7. 1 and 3 are in both of those sets, which gives us 2 elements out of the 8 possibilities. So let's imagine it's like an 8-sided dice or something we're rolling. say Sinead wins in the A set, 1, 2, 3, 4. Tyrone wins for B, 1, 3, 5, 7. And Mac wins for C, 4, 6, 8. So Sinead has a 50-50 chance of winning. Tyrone has a 50-50, and Mac has 3 out of 8 chance of winning, let's say. So the chance of both Sinead and Tyrone winning, so we're looking for, it has to come up with one of their common numbers here, would be 2 out of 8. There's 2 ways that those two could both win on that dice roll. Okay. So if these are independent, my left-hand side will equal my right-hand side. So I need to find the probability of A. So I just said that the probability of Sinead winning was 1/2. And the probability of B, Tyrone winning, was also 1/2, because they both have 4 ways to win. 4 ways out of 8. 2 out of 8, I can simplify to 1 out of 4. 1/2 times 1/2. 1 out of 4. Okay, so it looks like they are independent looking at that, doesn't it? The probability of A, if you look at A, it has 4 elements. So there's 4 ways to get A out of 8 possibilities. Same with B, has 4 elements. Yeah, so that certainly looks like they should be independent. Yeah. So let's have a look now. Are A and C independent? So,
How many books it has deduced?
I missed that, sorry.
How many books it has where deduced without
Deduce, like, figure out. So find out if they're independent. So let's do the same thing. The probability of A and C has to equal the probability of A times the probability of B. So we need to find the intersection of A and C. I'll go back up. A has 1, 2, 3, 4 in it. C has 4, 6, 8. So what's their overlap? 4. So it's only 1 out of 8.
Does it have to be the probability of C?
Oh, yeah, it should be, sorry. Force of habit, my apologies. Okay, and that would have to equal the probability of A, which is 1/2, times the probability of C, which is 3/8. So it's not looking good here. Is 1/8 equal to 3/16? No. So therefore, not independent.
Will they be independent?
They're not independent. And we have then our B and C independent. So I'm just going to have to scroll up to see what their overlap is. So B and C, do they have any overlap? No. So the probability of B and C has to be equal to the probability of B times the probability of C. So there's no overlap. So the probability of them overlapping is 0 because there's no way for it to happen. The probability of B is 1/2 times 1/3. 3/8, not 1/3. 0 is not the same thing as 3/16. So therefore they're not independent. Okay. Alright. So, this is more like what a question on your exam would look like. That last one was just getting used to using the rule. So, a group of 100 students was asked if they prefer playing sport or listening to music in their free time. The results are shown below. Okay, so there's 45 males. There's 45 males that like to play sport in their free time, 15 like to listen to music in their free time, for a total of 60. And it's 30 females that prefer sport to 10 females that prefer listening to music out of 40 total. So we've got to figure out, is a preference for a particular leisure activity independent of gender? So what we need to show is define A and B as particular things. What are our tests for independence? There's 3 of them that we looked at. We only used one of them in the last one. But if things are independent, we know the probability of A and B is equal to A times B. Oops, probability of B, that should be. What would you choose for A and B there? Not quite. So it's asked us the preference for your leisure activity is that independent from gender. So the probability of one would have to be your gender. The other one would have to be your leisure activity. Because those are the 2 things the question's asking us about. Yeah. So let's say A equals males, and B is likes sport. So the probability of A, I should just go straight into how many people, what's the intersection of males who like sport? 45. So 45 is equal to, what's the probability of A being a male?
45.
It wouldn't be 45.
60.
Yeah, it'd be 60 out of 100. So I just saw a typo as well. Over here, there should be 25, not 23. 60 out of 100. And then what's the probability of B? The probability that you like sport. Out of 100.
So that first 45 again?
Because we were looking for the probability of A and B, so the overlap, the intersection of A and B. A is males, B is people who like sport, so we're just looking for the number of people who like sport that are male.
Okay.
So we just got that 45 number from there. Okay. And technically that's 45 out of 100 as well, so we really should include that. 44. So we need to just check, does 45 out of 100, which we know is equal to 0.45, you put 60 out of 100 times 75 out of 100 into your calculator, what do you get? You don't know what? Just multiply it. So 60 divided by 100 times 75 divided by 100. Just staring at it, Tyrone. 0.45. Yeah, cool, isn't it? So, do you reckon we proved it? Have we shown that it's independent?
Mm-hmm.
I reckon so. We've shown that if you're male, sorry, your preference for sport isn't based on being male. Is what we've shown here. Now, if any of the aspects were out, it wouldn't work. But let's just try it for what about a girl liking sport? Let's just check that checks out as well, just to make sure we're not missing anything. It should work. So let's check for girls as well. So like I said, you don't need to actually do this in a real thing. If you proved once, that's enough. Hey, you could use either. But seeing as we used sport last time, let's use music this time. So let's let A equals female and B equals likes music. Okay. Probability of A and B is equal to the probability of A times the probability of B. So we're looking for the probability of female and likes music. How many people is that? 40 out of 100. So female likes music. Ooh, female that likes music isn't 40. So we want the intersection between female and music. So it would just be 10. 40 is how many people like music. 40 is how many females there are total. So the probability of being a female that likes music is 10 out of 100. The probability of being a female would be 40 out of 100, because there's 40 females. And the probability of liking music would be 25 out of 100. So let's put it in again, see what we get. Excellent. And now I haven't looked at the other rules for conditional probability. So remember there were two more. I'll just do it off to the side here. One of the other rules was the probability of A given B has to be equal to the probability of A. So let's just do a sneaky one of these as well, just to prove it works. So let's say A equals being, well, we're trying to say that the probability of you liking like your leisure activity is independent of gender. So let's say the probability of music, and then B can be the probability that you're male. What's the probability that you like music given that you're a male? So out of the males, what's the percentage of them that like music? Out of? Yeah, because we're just talking about males. So given that we're only looking at males, we're not looking at the females at all, so we ignore their data. Out of the males, there's only 60. How many like music again? 15. And that has to equal the probability of liking music overall. So what's the probability that someone likes music? That'd be 25 over 100. Looking at both of those, I can see that those are both equivalent to a quarter. 0.25. So therefore, we've tested it 3 different ways. Like, we didn't need to do this, but we have. Therefore, independent. We have proven our independence.
So what's A dash B? What does that mean?
A slash B.
Yeah.
That's what we did on Friday. So that means A given B.
So given that B has already happened, so in this case B is male, so saying given that we've already selected a male, what's the chance that they like music? Which is why we did it out of 60, because there's 60 males. So straight line means given. Okay, yeah, that's sort of all there is to a question like that. Like, you just need to prove that it's independent. Okay. The probability, I remember this question being annoying. The probability that a married woman watches a particular show is 0.4. So what show could we say that is? Married at First Sight. The probability that the husband watches the show is 0.5%, so 50%. So maybe this guy's a secret fan of Married at First Sight. The television watching habits are clearly not independent. Because if it makes sense, how many people do you know where they'd watch different, like if TV saw the thing that if one person's watching it, you kind of just end up sitting down and watching the same thing. The probability that the woman watches her show, given that her husband, that's a hard sentence, remember. The probability that she watches the show, given that her husband watches it, is 0.7. So what that means, the probability that the woman watches the show, given that the man does, is 0.7. You see how I've made that statement? The probability that the woman watches the show, given that her husband watches it. So we've already accepted the fact that the husband watches it. And given that, she has a 70% chance of watching it. What other statements can we make? So I've defined W as the woman watching and M as the man watching. There's two more statements. We've been given two more bits of information. What else could we say? So let's attach a probability statement to that. So the probability of what is 0.4? Sorry. And the probability of the man is 0.5. So we need to find the probability that both watch the show. Now they're not independent. So we've established that. Are you shaking your head at the maths, Tyrone, or just at something out the window? Yeah, it looked like it. Okay, so we need to find the probability that both the husband and the wife watch the show, and then find the probability that the husband watches the show given the wife watches it. So we've strayed away into some sort of, this would probably be a complex familiar, complex unfamiliar kind of problem. It's quite tricky. Let's go have a look at your, please tell me I've put it in here, your formula sheet. So these are our rules for probability. So these are our probability rules. So our first one is the one we did the other day, is that if you want to find the probability of A or B happening, it's just a probability of A plus probability of B minus the intersection. Now, do we want to know the probability of the man or the woman watching? Yeah, essentially. So we kind of need to find the probability that they both watch the show. But we don't want to know or. Or doesn't help us for this question. So I'm just going through my rules in order. Then we can look at the probability of independent events. Are our events independent? No. So that leaves us with just this last rule, conditional probability. So instead of A and B, we're going to be using W and M. So the probability that the woman watches it, given the man watches it, is equal to the probability that both of them do, W and M, divided by the probability of the man watching it. We know this first point. We know W given M, and we know the probability of M. Given that, we can rearrange that equation to find that last bit, the probability that they both watch it. This is a really common thing you have to do in your exam, is rearrange this formula. So let's go back to our problem. So we want to find the probability that both the husband and wife watch the show. So for A, we need to find the probability of the wife watching the show and the man watching the show. So the rule we're going to use for that is we know that the probability that the woman given the man, we already know what that's equal to, 0.7. We also know that must be equal to the probability of woman and man divided by the probability of man. I'm really hoping it's not too disconcerting to jump from A and B to W and M. I find in questions like this it makes it a lot easier to define what A and B is. If you don't define those A and B terms, it really gets hard to keep track of what's A, what's B sometimes. Okay, so let's look at this. We know what this value is. We know what that value is. That one's a question mark. So let's sub in our values. Probability of woman given man is 0.7. Is equal to probability of man is 0.5. Probability of woman and man, I'm just going to times both sides by 0.5. So therefore, the probability of woman and man is equal to 0.7 times 0.5, which is 0.35, or 35%. So the probability that on a given night, both of those people watch it is about 35%. Which, given that we're talking about married at first sight, is a little bit sad. Okay, do you guys have any questions about that step? Tara and Mac, you guys good?
Yeah.
Sweet. Okay, let's have a think about the next question. B, we want to find the probability that the husband watches the show given that his wife watches it. Can someone tell me, can someone make the probability statement of what we're trying to find? So, no, because that's the woman watches it given that the man watches it. We're trying to find the opposite. We're trying to find that the man watches it given that the woman watches it. So need to find. Can someone tell me the probability statement that we're trying to find? We're trying to find the probability of what? Yeah. Woman given man.
Same one as 0.7.
Sorry, we've done it the wrong way around. Because we're trying to find the husband watches it given that the wife watches it. So we're given the wife. Oh, sorry, we're not using H, we're using M. We want to find the probability of the man given the woman. Okay. To find that probability, we just we could go back to our formula sheet. We're trying to find a given probability, which just means we use that same rule. So the probability of man given woman is just the probability of man and woman divided by the probability of woman. So, do we know the probability of man given woman yet? Do we know the thing on the left hand of the equation, man given woman? Do we know that yet? No, so that's a question mark. Do we know the probability of man and woman? what is it? Yep, it's what we just discovered earlier. And then the probability of woman was 0.4. So that's just going to equal to 0.35 divided by 0.4. And what does that give us? 0.875, which is equal to 87.5%. Does that make sense logically? We found that if the man was watching the show, the woman would watch it 70% of the time. Now what we've found is if the woman's already watching the show, the man watches it 87.5% of the time. So does that sort of fit logically? Who's likely to watch the show more? The man. So does it make sense that if the woman is already watching it, wife is already watching it, the man would be more likely to watch it compared to if he's already watching it, the wife's a bit iffy about the show, so she's not like watching it as much.
So
Just if she's already watching it. Yeah. So if she sat down to watch TV, Married at First Sight, he's 87.5% chance likely to also watch that episode. Yeah. Yeah, which is what all that essentially boils down to. So these probability problems, they're interesting in that they're not super mathsy like some of the things you've done. Like if you think about some of the stuff we've learned, like finding the linear roots of a cubic, that has like so much maths involved in it. This stuff is a lot less about maths, it's just about understanding what's going on. If you understand what those three rules mean and what independent events are, these ones become quite easy to solve. You just got to like choose your rule, sub in, and rearrange. Okay, so can I get you guys to have a go at page 377, question 1, 4, 8, 10, and 13? I know. I spoil ya. Don't let anyone say that I don't. I will stop the recording there, so would you guys like to say goodbye?
Bruh.
Oh geez, everyone's shy today.